Imagine the most powerful explosion you can think of. Now multiply that by 1 billion, then add a few more billion just to be sure. You're getting close to the awe-inspiring power of a supernova, the grand finale in the life cycle of certain stars. These cosmic explosions are so bright they can outshine entire galaxies for weeks or even months. They're the universe's way of putting on a spectacular light show, signaling the end of one stellar story and the beginning of countless others. Supernovae aren't everyday occurrences, thankfully. They're relatively rare events in the vastness of the cosmos. But when they do happen, they leave a lasting mark on the fabric of space and time. These cataclysmic events are essential for the evolution of galaxies, the creation of heavy elements, and even the very existence of life. Supernovae occur in two main ways. The first involves massive stars, giants that live fast and die young. The second involves white dwarfs, the remnants of stars like our Sun, which experience a different kind of explosive fate. Both types of supernovae are fascinating in their own right. They provide astronomers with invaluable insights into the life and death of stars and the intricate workings of the universe. Let's dive into the dramatic life cycle of a massive star, one destined to become a supernova. These stellar giants are born in giant clouds of gas and dust, collapsing under their own gravity. As they contract, their cores heat up, initiating nuclear fusion. This process, which powers stars for millions or even billions of years, involves the merging of hydrogen atoms into helium, releasing tremendous amounts of energy in the process. However, this stellar party can't last forever. Eventually, the star's core runs out of hydrogen fuel. As the core contracts and heats up even further, it begins to fuse heavier elements, like helium, into carbon and oxygen. This process continues, creating a layered structure within the star, with each layer fusing increasingly heavier elements. Finally, the star's core is overwhelmed by its own mass. It can no longer withstand the crushing force of gravity and collapses in a matter of milliseconds. This collapse triggers a shockwave that travels outward through the star, tearing it apart in a spectacular explosion, a supernova. The energy released in this explosion is truly mind-boggling. It can briefly outshine the combined light of all the other stars in the galaxy. Not all supernovae arise from the death throes of massive stars. White dwarfs, the dense remnants of sun-like stars, can also meet an explosive end under the right circumstances. Unlike their massive counterparts, white dwarfs no longer have active nuclear fusion in their cores. They are supported by a different force called electron degeneracy pressure, which prevents further collapse. However, white dwarfs are incredibly dense objects. They pack the mass of the Sun into a volume roughly the size of the Earth. If a white dwarf is part of a binary system orbiting a companion star, it can siphon material from its partner. This stolen material accumulates on the white dwarf's surface, increasing its mass. As the white dwarf's mass approaches a critical limit known as the Chandrasekhar limit, the electron degeneracy pressure can no longer support its weight. The white dwarf becomes unstable and undergoes a runaway nuclear fusion reaction. This reaction consumes the entire star in a matter of seconds, resulting in a Type Ia supernova. These supernovae are incredibly bright and remarkably consistent in their luminosity, making them invaluable tools for astronomers. Supernovae aren't merely destructive events, they play a vital role in the grand cosmic scheme of things. In fact, these explosions are essential for the very existence of life as we know it. How so? Supernovae are the universe's primary source of heavy elements. The intense heat and pressure during these explosions forge elements heavier than iron, such as gold, silver, uranium, and countless others. These elements are dispersed into space, enriching the interstellar medium from which new stars and planets form. Without supernovae, our planet and our very bodies would be devoid of these essential building blocks. The calcium in our bones, the iron in our blood, the silicon in our computers, all were forged in the fiery hearts of long-dead stars. Supernovae also play a crucial role in triggering star formation. When a supernova explodes, it sends shockwaves through the surrounding interstellar medium. These shockwaves can compress nearby clouds of gas and dust, causing them to collapse and ignite new generations of stars. Furthermore, Type Ia supernovae, with their consistent brightness, serve as standard candles for astronomers. By measuring the apparent brightness of these supernovae, astronomers can calculate their distances with remarkable accuracy. These measurements have been instrumental in determining the expansion rate of the universe and the discovery of the mysterious force known as dark energy. In conclusion, supernovae are awe-inspiring events that mark the end of a star's life, but also herald the beginning of countless others. They enrich the universe with heavy elements, trigger the birth of new stars, and provide us with invaluable insights into the vastness of the cosmos. So the next time you gaze up at the night sky, remember that those twinkling points of light aren't just stars. They are potential supernovae, waiting to unleash their energy and shape the universe we call home.